Alright, so we got this 250 volt 4000 or 4500 microfarad capacitor, a standard capacitor, but it does have really good. It's very stable once it gets around 200 volts after you charge it, but it's at 247.7 and dropping slowly, and that drop is just mostly from the self drain of the natural part of the capacitor. It's not spinning, it's not taking any power. So now when I get it spinning right here, that's when it's pulling a load, and that's with it pulling a load, but it's barely pulling anything from the capacitor. I charged it up with this boost converter, connected with the supercapacitors with this battery, 9-volt battery, keeping these at 9 volts. So battery, supercapacitor that charges the high voltage capacitor to run the high voltage coils. Using my same switching method I used before, other than it's inverted because of the levitating idea I had. But it'll spin like this for probably a couple days at that voltage. Once it gets, like I said, once it gets to about 200 volts, the self-drain of this capacitor basically goes to a very small, in like the microamps. The self-drain is very low on this, which I would love to find some more that are like that. But they no longer on Moser provide this capacitor, so I have a film capacitor that I'm deciding on trying, and I would like to get them close to this 4-inch hole that I have here and get all these filled in with capacitors and then run them all in parallel or series, whatever, but they're going to be, well, I could go up to about 1000 volts with this switch where it'll still work without arcing. These mechanical switches that I've made are probably like the best thing for this. It's literally just a piece of aluminum with graphite foil for the surface contact, and then a piece of nickel with a magnet on there. The magnet obviously is there for the magnetic switching mechanism. And then I just hot glued it to the plate. I have my ceramic bearings in there with magnets, and that's what's helping the gap stay there and be centered and true. And this is just to add to the strength of the magnetic field to pull the rod up, because it's right at the limit to where it's going to attract it. And these are just temporary, just so I can get it suspended. These coils, I don't know if anyone remembers, but these are the same coils I used before. So with all of them in series, there was almost half a mega ohm of resistance. It's 42 gauge wire. There's a lot, like I think there's over 100,000 feet of wire per coil. I think it's like 143,000 or something like that per coil. There's 6 of them in series. So yeah, there is a ton of resistance between all of those. And that's why it requires this extremely high voltage for it to even run at that pace. And then I have a high voltage diode in between, or in line with the coils, so it doesn't want to charge the capacitor as it's running. I just want it to free spin on its own, and also it allows it to spin faster with that diode in there. So right here you can see it turn on. That's still the voltage of it with it running. Now if I go to where it is engaged, it's engaged right now, and that's the drain with it being engaged with the coils. And the nice part about running with this high resistance, nothing gets hot because there's, you know, very minimal amperage flowing through the circuit. So that's how much drain there is when it's, you know, full load on the coils with it turned on fully. Now if I let it go, that's what it is with it just running on its own, no load or nothing. I mean, I couldn't put a little load to it with my fingers, but you won't really notice it much. And the only problem with running it like this is the magnet interacting with the timing magnets does put a little resistance to the spin of the motor itself, but it needs to be there to move the switch up and down in order to make it contact. So it has to be there like that, and that with it being like this, I can get it to run down to about 60 volts, but it's you can't do it with a normal reswitch because, you know, the high voltage will just destroy the switch. I like my mechanical switching, and it's probably the best method for this purpose. Other than, you know, a transistor may work, but they're just, you know, not the greatest for extremely high voltages. I was debating on looking into them, but I just haven't bothered with it because they're so expensive. So at this point, I'm just gonna keep my mechanical switching method. But yeah, you can see how the voltage is almost barely dropping now at all. So it's getting close to the point where the self drain of the high voltage capacitor is at a minimum, getting close to a minimum, and most of the power is now being drawn just to power the motor itself. So this is without it spinning, and this is with it spinning. And even with it getting it moving, it barely phased that capacitor. So that's pretty exciting. Pretty cool. But for it to run on this capacitor, I started at like 100 volts yesterday, or like 120 volts before I went to bed. And I woke up in the morning, you know, 7 hours later, it was still spinning. I didn't look at the voltage, but then when I came home today, it was about 62 volts at the capacitor leads. So yeah, it can run down and run for like an extremely long time with, you know, I mean, it's not doing any work, obviously, but it takes hardly anything to power it. And for the sheer size of it, and there is such little friction on this motor that it takes nothing to turn it. Like, very little. I can't measure it, it's so little. But eventually I'm gonna figure out a capacitor design for the motor itself, but that's gonna be later on. I'm still kind of experimenting with it, perfecting it. But yep, this is where I'm at the moment, and see you guys later.